All right, let me switch gears and talk a little bit about laser cooling and trapping. It too, at the very, very beginning in the early 80s, wasn't clear what it would be used for. I knew of only one application, except the usual, which is, show off and write papers. And the one application knew about is once you had cold atoms, you could toss them up. They would be in free fall, they would turn around ballistically, and while they're in free fall, you can make a better atomic clock. And so when I first got to Stanford after leaving Bell Laboratories, this was one of the early experiments we did with Mark Kasevich, Early Reese, who's professor at the University of Strathclyde, and Ralph DeVoe. And so this was the first experiment that showed indeed you can actually make a better atomic clock. And that turned out to be very useful. Another closely related thing is in the tossing of the atoms upward, and they turn around ballistically, if you then irradiate with coherent pulses, you can take one atom, quantum mechanically split it, so one part of the atom is going up faster than the other part, and then put in another pulse to reverse the velocities, and they catch up with each other and they recombine. So in this schematic picture, where height is on the y-axis and time is along the x-axis, really just going up and down, they can separate, and in this case for up to a millimeter or so. And the first atom interferometer was made by Mark Kasevich, who's now a professor at Stanford, and myself. And there was a series of papers that came out, noting one that we used this atom interferometer to measure the acceleration of gravity to about 9 decimal places. The limitation was not the interferometer, it was actually comparing to another way of measuring gravity. Now it turns out that in my current job, it dawned on us that you can reanalyze this data in a different way, and you can write the phase shift of this atom interferometer as 2 parts. If you just stick in a normal Lagrangian and they just say what you find that one of them is due to a time dilation effect. This is the special relativity effect of the one part of the atom is going faster than the other part. And this first part is one part of the atom is at slightly higher gravitational potential than the other. Now, the separation isn't very much, and the velocity change is not very much. It's 3 millimeters a second. But the fact is that if you write this out, there's an inherent clock frequency that depends on the entire energy of the atom, and that's something deeply embedded in quantum mechanics. The actual frequency is not the frequency of, let's say, 2 internal states, but it's the entire energy of the atom. And in this case, one can show that the appropriate frequency, we believe, is the quantum frequency, which is beating at a very high rate. So if interpreted in this way, this is a measurement of the redshift anomaly. This is just the parameterization of a breakdown of the redshift. If beta is 0, everything is good. And of course, we didn't see any departure, not of course, but we didn't see a departure from the breakdown. But it turns out an atom interferometer like this is a much better test of Einstein's gravitational redshift. So that was kind of fun. At the early days of laser cooling and trapping, it wasn't obvious to any of us that you can actually achieve Bose condensation, but that was realized, I think 1995 or 6, something like that, by Eric Cornell and Carl Weinman at Gila, soon thereafter by Wolfgang Kertele at MIT, and so another Nobel Prize. And so the value of a Nobel Prize is how many other Nobel Prizes it gets. And so it has not only using laser cooling and atom trapping techniques, you can achieve Bose condensation. It turned out to open a wide window of other things. Studies of degenerate Fermi gases, quantum transitions like Mach transitions, and many other many-body effects. So this is just a measurement of the velocity spread. But Eric, you're going to talk about this soon, so I'm not going to mention it. Okay, so Eric is here. But I want to talk about something else that Eric and I have worked on, and that is having to do with what are called quantum phase transitions, but a very unusual phase transition into what's called a topically ordered state. Now, normally all phase transitions, liquids to solids, liquids to gases, for example, or magnetization, can be described by a Landau symmetry breaking. And for example, liquids, if you have a big vat of liquid and look at the symmetry here, and you just move it over here, it's the same. If you have a crystalline solid, if you have a symmetry over here, you have to move discrete steps away of lattice parameters, and so the translation symmetry in a crystal is discrete. So there's a change in symmetry, which describes all phase transitions. And there's a locally defined order parameter. For example, liquid to gas, it's the density of the material, and in magnetization, it's the net magnetization, et cetera. So it was believed that all phase transitions would be described by symmetry breaking and by order parameters. And it turns out that that is not true, that there are states which are called now topological matter, and the prime example is electrons when they go into the fraction quantum Hall regime, and they can't be described by either a local order parameter or long-range correlations. And then a whole new set of quantum numbers has to be put into play. And these are weird things because you have a hugely degenerate ground state. The quasi-particles exhibit, in this case, fractional charges and fractional statistics. They're no longer fermions and they're not bosons. They can be weird things. And these topically ordered states are deeply entangled many bioquantum states. So it's really a very different state of matter, not like we've seen before. And that is the reason why the fractional quantum Hall effect was what it is. You know, you think with the Hall effect, why would they give a Nobel Prize, a second one, for a fraction of a Hall effect? But it's a big deal. But there's an analogy between electrons in two-dimensional, very low temperatures. They're in 2 dimensions in a very, very high magnetic field where you get grossly degenerate electrons circling in cyclotron orbits with atoms, very cold atoms, in the ground state, starting with a Bose-Einstein state and rotating them up. And the analogy of the magnetic field, the counterpart in these atoms is the Coriolis force, where in this case the P momentum becomes the canonical momentum, including the vector potential. Coriolis force, you have this thing here. The cyclotron frequency corresponding atoms is the harmonic trap frequency. Kluman interactions, well, they're interactions of the atoms. There's contact interaction. The magnetic flux quantum associated fractional quantum Hall effect becomes vortices. And this is the Hamiltonian for the quantum Hall effect. This is the Hamiltonian for the rotating atoms. They're identical. And so one would think that you can get another atomic system. There are problems. If you have a macroscopic number, it turns out the gap, this lower energy state, remember this is a quantum transition into a new low energy state, but the gap in a macroscopic number of atoms is just too teeny tiny to be observed. And so one can finesse it by actually taking not 1,000 atoms, but maybe 5 atoms or 4 atoms. And you get 4 atoms, but you put 4 atoms, or as close to 4 atoms as you can possibly manage, into, let's say, 1,000 little harmonic wells. You use optical tricks to take this spherically symmetric, this is now 2-dimensional, so the atoms are confined only in 2D. They're separated in the 3rd dimension. They're in the lowest ground state in the 3rd dimension. You distort the harmonic potentials. You begin to rotate them up, and you give them angular momentum. And it turns out that we believe we have been able to see this, but now with an average occupancy number of 5. And it's submitted to Science. It came back. We're responding to the referees. One of them might be here, but I'm not allowed to ask him. In any case, it is a weird state. If you look at the density, probability density for just 2 bosons in this new ground state, so-called Laughlin state, it looks like this. But if you ask a different question, if you ask if one atom is over here at this point where my arrow is, what's the probability of finding the atom anywhere? If it's a normal Bose condensate that's weakly interacting, the probability of finding an atom is given by some distribution that kind of looks like the shape of the potential. If you find another atom, it's given by the same thing. But over here, they're strongly correlated, and the probability of finding another atom, the second atom where the first one is 0, and it's all shoved over to the side. Okay, that's one example. There's many other examples. The phases do weird things in these states. Okay, so the tools of cold atoms are able to probe many, many things, and because the atom technologies are so powerful, you can actually probe many biosystems in ways that the normal condensed matter physicists using electrons and other things have not been accessible to. And so it becomes a testing ground for many-body quantum interactions. Laser trapping and cooling actually has an impact on biology. This is an early example of this. About 1990, we showed that you can actually hold on to a single molecule of DNA by gluing it to a little polystyrene sphere. This molecule of DNA is visible because you put fluorescent dyes on it, and then you use an optical trap to hold on to this little fluorescent sphere. And this particular movie, this long molecule of DNA, is in a solution of other polymer molecules, other DNA that are not stained. And the reason it's doing this, it's shrinking because this is a big rubber band, if you will. It's a single molecule rubber band. And so it's able to follow these tortuous paths because there's a tube that's defined by this polymer, and we were actually testing a theory called reptation that Dijen proposed. And when he got his Nobel Prize, he wrote reptation on a blackboard with smile line pointing to it, and that's how I heard about it. And so it turned out that there wasn't direct evidence for that, and this was the first example of really direct evidence of reptation. So it kind of sucked me into polymer physics and biology, but a lot of water has passed under the bridge. And so I want to now ask a question, is life based on the laws of physics? Well, if you're a physicist, you would say, of course it is. But now a quote from a lecture, very famous lectures. From all that we've learned about the structure of living matter, we must be prepared to find it working in a manner that cannot be reduced to the ordinary laws of physics, because the construction is different from anything we've yet tested in the physical laboratory. It's not because there are new physical laws, it's because of that. And Erwin Schrödinger said that in Dublin in 1944. I guess that's a bad word here. No, it's okay. Dublin's okay. Okay. Anyway, he studied in Dublin in 1944, and so what was he talking about? Well, if you look at any man-made machines, they are actually designed to minimize friction. You know, there's ball bearings and oil and grease and things like that. In an organism, and the machines now are molecular scale, that machinery is embedded in a viscous fluid, and there's friction and thermal fluctuations, and they're tied hand in hand to the fluctuation dissipation theorem. They're enormous. For example, the law of motion is not F equals ma. It's F is proportional to velocity. As soon as you stop pushing on something, it stops. If it's molecular size, it stops in a fraction of a microsecond. But it doesn't really stop. It sits there and jiggles around due to Brownian motion. And so very, very different laws. And so the question is, how does nature fight this? So there's some articles being published about this. But let me just point out that the lore, this is an E. coli. And in E. coli, you have these flagella. And if you now look at the, you know, they move around by circulating these long strings. But if you blow up this little motor behind there, you find a conceptual diagram of the motor mechanism of an E. coli. And it's a flagella filament. It's a motor based on a proton gradient. And you see things like bearings and rotors and stators, and you think this is like a little machine wiggling around very nicely. But it can't be that way because this is embedded in a very viscous, highly dissipative stuff. And so what is really going on? Even that machine, as we later find out, is not so good. So I'm going to describe one machine that we have been studying. Oops. And this is the ribosome. The ribosome takes messenger RNA. This is a 5-angstrom model of it. We now have atomic scale resolution. In fact, the people who developed that have gotten a recent Nobel Prize. This is the scale model of this colored ribbon here is messenger RNA. And that's the code that is translated from the DNA into messenger RNA. And these things here, this green thing and that red thing that you saw in the cutaway, are transfer RNA holding amino acids. And then what they do is, this is a blow-up of that transfer RNA. And on the transfer RNA, on this little tippy top, there's a little amino acid. And that way down here at the bottom, if you blow that up, there are these 3 bases, RNA unpaired bases sticking out, looking for a home. And the idea is that if you have the messenger RNA, which has 3 bases, and if these bases are the complement to these bases, they will sit and match. And the hydrogen bonds formed by these bases then say, aha, here comes an RNA. Am I sticking on the right messenger RNA? If I'm not, I'll fly away. If I am, I'll stick, and I'll proceed and stick my amino acid in with this growing chain of amino acids that then fold and make a protein. So that's what they all tell us in biology when we learn it in high school or college or whenever. But here's an issue that was known. The wrong RNA, this is a very good machine. It doesn't make many mistakes. It makes a mistake maybe once out of 10,000 times. And then if you ask the question, a more quantitative question, is the binding energy of these weak hydrogen bonds enough so that if you have these 3 hydrogen bonds, it sticks a little longer, so it makes the right coupling? Or if one of them isn't made, if, let's say there's a mismatch in one of them, is it enough to actually have it linger and stay? And the answer is no, it's not even close. If you have a 1-base mismatch, there are in fact some cases where the number of hydrogen bonds could actually be the same or larger. So this was known, even though it didn't show up in the textbooks, it was known by the biologists by the mid-60s, including Wally Gilbert, a former theoretical physicist, wrote a paper and said, look, the energetics, the base binding is not enough, and so maybe it makes a discrimination based on shape, like you can't fit a square hole, a peg in a round hole. And so the idea here, it was then elaborated further by Dan Koshland, who noted that if you have a protein and something that's stuck on the protein, maybe the protein will actually change its shape. So this was then applied. Suppose this is the bottom of the ribosome, and this is the region where you're going to look at the bases, and here comes this transfer RNA, and it's matching down here. Could it be that if these things match very well, that the bottom of the ribosome, if they don't match, they may be sticking out. If they do match, they're not sticking out. And if they're not sticking out, maybe the ribosome closes in around it, makes a tighter binding. So it's not really the base pairs, if they just, sticking out at odd angles, the ribosome couldn't close in around it as much. And so that was proposed. Maybe that's the mechanism. But it was just a proposal. Another theoretical physicist, John Hopfield, came along because he was intrigued by why this machine was so good at what it did. And so he looked at this and said, look, here's a cartoon of a ribosome. This is the messenger RNA. These are the bases. Here you got one transfer RNA, and this triangle is an amino acid. So in floats, it's in the soup of all these other transfer RNAs with their amino acids, and it's got this other this oval is a protein that helps it. I'll tell you in a minute what it does. Anyway, so this guy comes in and says, am I the right one or the wrong one? If I'm the wrong one, I'll throw it back out and wait for the right one. And then when the right one comes along, it joins the 2 amino acids together, and it's on its way to making a protein. So Hopfield says, maybe it's more complicated than that. And he said, suppose there's another state of the ribosome. I don't know what it is. He was a theoretical physicist. And he said, I suppose there's another state. I don't care what it is. And suppose when you go from this state to that state, it's irreversible. It's one way. Then what can you do? Well, over here in this first step, which he called selection, you said, you asked the question, am I the right transfer RNA with the right amino acid or the wrong one? If not, I throw it back. If I am, proceed to next step 2. Step 2, you ask the question again, am I the right one or the wrong one? If I'm the wrong one, I throw it back out. If I'm the right one, I proceed to joining the two amino acids together. Why do you need it to be irreversible? Because he shows just by rate equations, if it's reversible, you don't get better fidelity, just math. But it's irreversible, it makes two independent tests that are that you multiply together. Suppose there's a 1% chance of making a mistake in the first step, and there's a 1% of making a mistake in the second step, then it's the conditional probability, the overall probability becomes 10 to the minus 4. Okay? So he told me, he was up there giving this talk in 1974. He didn't tell me in 1974, but he said, and there's in the back of the audience who said, okay, Mr. Theoretical Physicist, that's what you think. Oh, by the way, he said, in order to make it irreversible, one good way to make it irreversible is burn some energy. Break a chemical bond, okay? And so this guy in the back of the stand says, guess what? You're right. They're burning some chemical energy. They're taking a phosphate bond, GTP, and turning it GDP by breaking, that's the energy realm of biology, breaking a phosphate bond, ATP to ADP, GTP to GDP, okay? So it breaks a phosphate, so this guy says, we just discovered it's burning energy. It's breaking phosphate bonds, okay? So kind of cool, right? Definitely kind of cool. So anyway, now fast forward another 20 years. Again, we have now atomic structures of this ribosome, the messenger RNA, the transfer RNA, and these two guys have to get really close to one another and embed themselves. So with these atomic structures, we said, okay, we now have detailed atomic structures, but they're static pictures, and they're not catching the ribosome doing its thing, and they're not catching it moving. So we thought, well, why not put a fluorescent dye molecule on the transfer RNA in that hook region where there's lots of space so it doesn't mess up the biology, and we showed that, yes, indeed, it's going in and it doesn't slow up the rate of this. And let's say you put in another transfer RNA, and if you're using a laser to excite this dye molecule, but if this dye molecule is close to this one, near field, so its oscillating electric field will then excite that dye molecule, and you get, instead of seeing mostly green light, you'll see mostly red light. So by just looking spectroscopically at the color of the light between red and green, you can tell if this transfer RNA has gone into the ribosome. Well, so you ask, what's so good about that? Of course, we know it happens. The hope was it goes in stages. It may spend some time over here, it may walk over here, it may walk over here, and so you can see progressively brighter values of the transfer RNA. And sure enough, that worked, and we saw progressively brighter things, and we can see it going in steps, and we can see it fluctuating around. Now, I'm sorry for this other detail, but it's necessary. So here's the coding region, where it's sticking its 3 RNA down looking for its messenger RNA. This is the transfer RNA. There's another loop on the ribosome. It's called the Sarsen ribosome loop. It's just this double loop of RNA. And there's this protein called EFTU. The protein EFTU is holding this unit of fuel. And it turns out that this unit of fuel does not get burned until this structure of the RNA touches this protein near the spot where the EFTU is. Okay, so that much we knew also. So that was good. So the key is what was going on. So here's what we found using this resonant fluorescence transfer. With the proper base pairing, it causes the ribosome to wrap, just as was noted before. That was shown by X-rays. And we showed that once it wraps, it actually positions the transfer RNA a little bit closer. So there's a little bit step up in the fluorescence resonance energy transfer, a little bit more red light. But you notice how I've drawn this picture. This loop has got to touch this protein about here. But I've drawn it so there's a gap. Now, here you've got the wrapping. We compared the correct matching base pair with one that just had one base mismatch. It was 2 hydrogen bond difference. And what we found is that you say, okay, what was the original idea of this? That if you have this wrapping and all of this, the wrong guy is more likely to fly off than the right one. That's true, but only 3.7, less than 4 times more likely. Hardly anything. So what the heck's going on? So what we found overall in this first selection, there's two steps. There's selection and there's proofreading. The first selection process, we found between these two RNA, there's a 250-fold difference in selection. But it's only 3.7 times more likely for the wrong one to fall off than the right one. So what did it do? As I said before, it positions it so you haven't finished the job yet. It could have just wrapped it and said, clunk, you have done with first step, proceed to next step 2. Nature didn't do that. It said, clunk, I'm over here, I'm not quite over here. Why did it do that? Because nature is very smart. It used another selection mechanism. Okay, and what we found is that the correct tRNA was positioned slightly differently, and there was a 12-fold times more likely chance of making, I missed a digit there. There's 120 times more likely chance of going forward, okay? So why is that? 120 times more likely to make the stabilizing contact to keep the right one there than the wrong one. The difference of it flying off was only 4 times different, okay? Why? Well, initial selection is based on the probability of rare statistical events. Suppose this transfer RNA is wobbling around, Brownian motion, centered about this position, and only a large fluctuation, a very rare event, pushes it over. Why do we know it has to be rare? Because this is taking tens of milliseconds, and this thing is wobbling around on a nanosecond, sub-nanosecond time scale, okay? So it's really fluctuating like crazy. And then finally it makes this large fluctuation, and it goes. So if this is the wrong one, it has to move over some distance out to the tail of the distribution. And you say, well, you can say that it's probably some exponential type of tail. We actually did a little more quantitative. This Dane Mohanty is now doing much more quantitative stuff. But anyway, it's an exponential tail. This is the attempt frequency. It's wobbling around. If you put in the right one and it wraps more tightly, it positions it slightly differently. We see this in our measurements. And so what happens? Well, the probability of making this statistical fluctuation is just changed by a little bit. So what have you done? You've actually put the difference in positioning in the exponent where it does the most good. And so nature is using rare statistical fluctuations to make a small difference into a big difference, okay? And now you can ask a question, and this part's speculative. Why is the transfer tRNA so big? After all, the amino acid, just this little guy up here, and the coding region's down here, and this is 90 angstroms. Well, it's a big lever, because the wrapping is down at the bottom, and it may be just a big lever, okay? But this is speculative. The rest is more quantitative. So nature's kind of neat. We've studied other enzymes, and we found that other enzymes don't fight fluctuations. They use them. They use them in their enzymatic activity in a very intimate way. And this is not just the first one. And so I'm beginning to believe on 2.5 data points, 2.5 different enzymes, that it seems to be this way, and other people are beginning to look at other machines, and it seems to be this way. So Schrodinger was right. These machines aren't anything we've tested in the laboratory. We don't make machines that wobble around due to statistical fluctuations, okay? But they have to live with it. All right, now why would a scientist want to leave academia to become a director of a DOE National Lab or U.S. Secretary of Energy? I've asked myself that often. No, seriously, it's because of something that I began to talk about around, I think, 2002, 2003, and it slipped things in here and there. And it was the fact that I was getting increasingly concerned that the climate was changing, and it was caused by humans. And this is the temperature record of the world temperature average over the last, 1880, 2009. And now, I will be the first to say that we do not understand these little 10-year ripples and bumps and things like that, because it's very complicated. There are very complex interactions with the oceans, with the clouds, and other things. However, let me say that even though we cannot predict yet what the temperature will do. We did not predict that there was a plateau over here. It seems to be, it looked like it might even be going down, just as it might have gone down. It did go down over here, but it seems in 2010 to be about as warm as the hottest. So the temperature is increasing. And so let me say something about not the 10-year or 15-year cycle, but about the 100-year cycle. So the temperature, energy input is constant, that's from the sun. The energy output is less because of the greenhouse gases, carbon dioxide, water that follow, but so there's less heat energy out, so it's more energy comes in than goes out. Then you might say, well, wait, what about assumption number one? Is the energy input really constant? And can the temperature rise be due to an increase in solar energy? So here's the temperature average, and the solar energy actually has 11-year cycles. And now, in the last years, we have excellent satellite data on many, many things. For example, we have incredible satellite data on the fact that can measure masses, and using two precisionally tracked satellites. So when the satellites go over a mass like Greenland that's got a lot of ice on it, versus Greenland in the summer versus Greenland in the winter versus Greenland snow melting, glaciers melting, we can actually see the melt increasing, decreasing. The amount of ice mass is decreasing, but it's not only decreasing, it's got at least a quadratic dependence to it. And the precision is so good now that you can see the difference between winter and summer. But here in this case, this is the sun's energy reaching the top of the atmosphere. Where the satellite is, it looks pretty constant. So at least in the United States, we have skeptics, and they say, well, that's because you haven't included sunspots. And sunspots are the reason why the Earth is warming up. So what about sunspots? Well, we measure those too. We measure the ions, the sunspots, we measure the solar flares, we measure radio emissions. They're all the same. Okay? So sunspots aren't the reason for it. So that's that. So here it is. It's an energy conservation sort of thing. You know, energy input in same, less energy out. Less. You know, you eat the same, you exercise less. Guess what happens? So the point here is that there's no real credible argument that the Earth will not heat up over a 50 or 100-year time scale because of this. Okay, so that's the issue, at least in my mind. So now, how much will it heat up? Well, we have models. They do have some uncertainties. But let me also say that the Earth will not heat up until you warm up the deep oceans. The oceans, down in the bottom of the ocean, is considerably colder than the top. I know this firsthand. I spent 4 months of my life trying to stop an oil leak in the Gulf of Mexico. And, you know, the Gulf of Mexico on the top was 85 degrees, the water. Down below, it was near freezing. Okay, so then there's a very slow mixing between the top of the ocean and the bottom of the ocean. And in that very slow mixing, the mixing time is about 100 years. So here you have heat, the same amount of heat coming in, less heat going out, but until you heat up the environs, it hasn't reached equilibrium. So you don't get to know what the new equilibrium temperature is until 100 years afterward, even if you shut off all carbon emissions. So that's another thing that I think many people don't fully realize. They say, well, wait, why don't we wait to be sure? But there's this lag of what the world is really going to do for about 100 years. So that's another problem. And so that's what's going to happen. The predictions, well, they're less certain than our measurements of what is happening. And to quote the great American philosopher of the 20th century, Yogi Berra, catcher for the New York Yankees, he said, predictions are hard to make, especially about the future. But with that caveat in mind, since I looked at something that might happen locally over here, you will expect increased coastal erosion and flooding, stresses being biosystems, things like that. Greater storms. The storms will come not evenly, but they will be heavily weighted towards more downpours. Because it would be warmer, there would be more precipitation. But despite the fact that there's more precipitation, it's not coming at the right time, and so in these dark brown and yellow areas, these regions of the world become severely water stressed, including large parts you're okay. You're not going to be water stressed in drought ways, maybe too much water. So what's happening is that there will be changes in the Earth, and to what extent we don't really know. The detailed local predictions are less certain for sure than the global average, as you can well understand, but at least there's a possibility that we're at great risk, and so it's just prudent insurance. Maybe we should do something about it. All right, so now climate science, as years go by, each year, progressing year, they get more and more nervous, and I am, while others remain unconvinced, and they said, look, if you take action now, you'll hurt the economy. Let's just wait to be sure, and that's okay. But I think this is a false choice, partly because I think it's inevitable that we will live in a carbon-constrained world, and so the development of clean energy technologies and the rebuilding of an energy-efficient infrastructure is actually a job growth thing. It's a demand of something really needed that can actually spur economies all over the world, and it will be essential for our economic prosperity. So what is the United States doing? Well, we don't have a comprehensive energy and climate bill yet, but during the recovery of this deep recession, the U.S., under President Obama and Congress, have passed the Recovery Act, and we're spending $90 billion investment in clean energy. And so that includes the promotion of energy efficiency, development of new low-carbon energy sources, and spurring energy innovation. The Department of Energy, aside from its usual budget of $26 billion a year for a variety of things, we got put upon us another $32 billion to be allocated in 2 years. We've done that. It's all allocated now. Never in my life have I had so many friends. But we think these are wise investments because they're investments in a future and they're investments in energy infrastructure. However, a lot of the things like putting insulation into homes and buildings, we know how to do. We should do this, but we also need new breakthroughs. And science and technology have given us solutions in the past when things looked bleak, and I think they're going to do it again. They have to. We have no choice. So let me give you one example. This is a plot of the world production of grain from 1960 to 2005. During that time, the population more than doubled. The world population more than doubled. And in 1968, a best-selling book was written called The Population Bomb, which the author predicted that there would, despite any massive programs to feed developing world, there will be mass starvation. Tens, if not hundreds of millions of people will starve to death. In 1970, a fellow by the name of Norman Borlaug was awarded a Nobel Prize for developing dwarf strains of wheat. So what did he do? He bred strains of wheat so that they were smaller, so that they could be resistant to pests, but they could also grow and have higher yields, and they could take more fertilizer. And so what that meant was that the grain supplies per acre, the grain production per acre in Mexico, India, Pakistan actually increased 3- to 5-fold. Okay, so this was not only rich countries having technology, this actually was disseminated into developing countries. And as a result of that, the amount of land put under grain production went like this. It actually declined slightly. The amount of grain increased 4- or 5-fold worldwide. And remarkable. So this, now people are starving to death, but due to a distribution issue, due to an economic issue, not due to the fact that we can't grow enough. Okay. So there's another thing that happened in the turn of the other century, the 19th to 20th century. Europe was facing mass starvation. In a scientific society, the president of the society is in Britain. It wasn't the Royal Society, I'm having a blank now, but he gave a speech and said, we're going to face starvation. Europe was using fertilizers at the time, but the supply of fertilizer, at first they used bird guano, that's bird doo-doo, and they ran out of that, and then they used saltpeter that was mined from South America. And they said, well, look, the saltpeter reserves are going to run out, and then we're in real trouble. And it was predicted perhaps we will begin to see starvation in the 1930s. And this person said, it's up to the chemists to invent artificial fertilizer, and that could save us. And so that call for this invention led a race, actually, of chemists. And finally, Fritz Haber developed a process to synthesize ammonia from nitrogen from the air. And Haber, in a high pressure process, actually made it commercially viable. When Fritz Haber got this achievement, he was awarded a Nobel Prize. And then Bosch was awarded a second Nobel Prize about a decade and a half later because the invention of fertilizer was considered that important. Now, in about, I think, 2007, a third Nobel Prize was given to catalytic chemistry. And it said, at last, we were beginning to understand the Haber-Bosch process. So, so 2.5 Nobel Prizes for the invention of fertilizer, because it was a big deal, all right? So bear that in mind again for the young people. And so in the Department of Energy, we are a funding agent. We have funded more the work of more Nobel laureates than any other funding agency in the world. It's over 80. But we are also now trying to get some of these very, very smart people to try to figure out if we can solve the energy problem. And there are two innovative things we've started. One is called Advanced Research Projects Agency Energy. It's modeled after a US organization called ARPA or DARPA, which this is called RPE. And the idea here is we would invest in very short term, typically 2 years, at most 3. Here's a couple $1 million. You've got some crazy idea. It may fail. We expect 2/3 of them to fail, but we're hoping at least 1 in 10 will be a home run, and maybe 1 in 30 could be a grand slam. In the baseball vernacular of the United States, this is game changing. So we, instead of funding incremental research, we are specifically looking for wild and woolly things. And the other thing is these energy innovation hubs. So let me, and as with radar, the research aimed at solving energy and climate problem, I think will lead to very important discoveries in fundamental science. So here's one example in RPE. Energy storage is a big deal. There's on the large energy storage, even at a megawatt, the best things that you can store energy is pumping water up a hill or compressed air into a cave, believe it or not. Batteries are not commercially viable. But even batteries at the megawatt hour scale and megawatt power scale would do a lot. And do we have those? Well, if you think of the lithium-ion batteries that are going into the versions of today's electric cars, they're not really too much different than the lithium-ion batteries in your computer. They just take these little things and they just pile them on top of one another, and they're just massive. They don't make a big battery, they make lots of little ones. And so it doesn't scale right. So a professor at MIT said, well, look, suppose we have an electrolyte of metal salts, and you have two metals, one type of metal, bismuth, let's say, and another type of metal, magnesium, and it's hot, so it's all molten. But the metals and the electrolytes, the salts, have different densities, so they just kind of float on each other. And the death of a battery is actually at the interfaces and things like that. So they're separated by gravity. So this one scales because you can make it a swimming pool size. And you charge it by passing a current, just as you would in aluminum purification. You have an aluminum salt and you're plating out the aluminum metal and you're releasing. In fact, that's what inspired this person to invent this. He said, well, why not have it go to another metal? And in that case, potentially this battery can cost $50 a kilowatt hour instead of $500 a kilowatt hour. In the standard large bulk batteries, the sodium ion batteries we now have, or in lithium car batteries, $1,000 a kilowatt hour. So you get more than an order of magnitude increase. He built a little test tube version of this and it worked. So he's scaling it bigger, and maybe it'll work, maybe it won't, but it's a new idea. So we're funding lots of new ideas, and we're specifically targeting where the gaps. Semiconductor, wide bandgap semiconductors make much more efficient converters, AC to DC, and much more efficient electronic converters. it seems to have ignored funding, and so you're going to throw tens of millions of dollars at that. And so the group doing this are actually looking around and seeing technically where there are gaps. The other thing we're doing is these energy hubs, and they were actually modeled after what I saw. Now, what I saw, I'm not that old. I didn't work at Los Alamos, MIT's radiation lab, or the Met lab, but I used to say I'm old enough to have known people who actually worked there, but now you too are old enough to have known someone who worked here. Roy Glauber was at Los Alamos, and Roy, you know, I would sit at his knee, he would tell me stories about Los Alamos. Dan Koshland, not too many. Dan Koshland told me a lot of stories about when he worked with Glenn Seaborg. And so I learned from that and found out how they did work. And for example, in Seaborg's laboratory, he was in his early 30s, he was put in charge of separating plutonium. This guy knew exactly what was going on that day and the previous day. He'd write in his journal. I was looking at his journal entries. He said, okay, we did this, this, and this. That didn't work. This worked. We'll see what we're going to do next. This is a brilliant scientist who's actively managing, and the collective group of them, and I think it was also, well, Roy can talk to that, what it was like in Los Alamos, but it was this best scientists were actively managing going forward, and they were actively saying, we can't do it at the usual pace. There is a real urgency. And so can we get this done here, now, today? Because I think there is a real urgency. I worked for 9 years at Bell Laboratories. I used to live in an original farmhouse right where my little arrow is. Life was good. I would hop over the fence, walk to work, and you know, I didn't have to come home until very late, and that was all good too, and except for people I was close to. And anyway, never mind. Anyway, it was a spectacular place, and when it turned on something, it really made things happen. And for that reason, things like the transistor were not only invented but developed there, the silicon photocell, the laser, the CCD detector, satellite communications, cell phone technology, information theory, all these things came at Bell Labs. Very, very special place. Managers, one of the big secrets is the managers were the best scientists, and they were the best scientists fairly young. They were put in the managerial positions in their middle 30s and then kept in there, and when they lost their ability to do science, they were eased out of management. They would go and retire at a university like Stanford or something. So anyway, but in any case, there was something about managers actively invested in managing this that made it happen, at least I believe. So we are trying to recreate that. And so I leave you with this last thought about why I left science, and I did leave science. Well, not really. I do it in a parallel universe. And I leave you with this thought that was Carl Sagan, something Carl Sagan wrote. But in 1990, Carl Sagan convinced the NASA engineers who were responsible for Voyager 1. Voyager 1 went by Jupiter, Uranus, Neptune, and Pluto. And when Voyager 1 was way out here, turn the cameras back and take the last parting shots of the planets, including Earth, before it left. And this is the picture it took of Earth, this little pale blue dot of light. So what he said, what he wrote about, this is a very abbreviated version. He said, look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you've ever heard of, every human being who ever was, lived out their lives. Every hunter and forager, every hero and coward, every young couple in love. Oops. I don't know why it does that. Every young couple in love, every mother and father, hopeful child, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. Our planet is a lonely speck, the only world known so far to harbor life. There's nowhere else, at least in the near future, to which our species could migrate. Like it or not, Earth is where we make our stand. So, I leave you with that and an ancient Native American saying that says, treat the Earth well. It was not given to you by your parents, it was loaned to you by your children. So, we're in danger of breaking that trust. So, that's why I left science and biology. Thank you.